Oh, something in the universe is colder than the void between galaxies. Colder than the cosmic microwave background, that faint thermal whisper left over from the Big Bang. And it isn't deep in some remote corner of intergalactic space. It's a cloud of gas roughly 5,000 light-years from Earth, drifting inside our own galaxy, shedding heat so efficiently that it has become the coldest known natural place in the observable universe. That place is the Boomerang Nebula. Located in the constellation Centaurus, the Boomerang Nebula is what astronomers classify as a protoplanetary nebula, a star in the late stages of its life, expelling its outer layers before it collapses into a white dwarf. At roughly 5,000 light-years away, it sits well within the Milky Way, close enough that multiple instruments have studied it in considerable detail. The nebula spans approximately 1 light-year across its central outflow region, a modest scale by cosmic standards. But its temperature is anything but modest. Measurements place the gas in the Boomerang Nebula at approximately 1 Kelvin, 1 degree above absolute zero. For context, the cosmic microwave background radiation permeates all of space at about 2.7 Kelvin. That background temperature represents the baseline thermal floor of the observable universe, the residual heat from the Big Bang, now stretched and cooled across 13.8 billion years of cosmic expansion. The Boomerang Nebula sits below that floor. It is, by this measure, colder than the universe itself. That is the contradiction at the heart of this object. In a universe where even the emptiest void is bathed in 2.7 Kelvin radiation, how does a cloud of gas around a dying star manage to cool below that ambient temperature? The answer is not exotic physics. It is, in a sense, the same principle behind a pressurized aerosol can feeling cold when you spray it, scaled up to stellar proportions and sustained over thousands of years. The process is called adiabatic expansion. The central star is expelling gas at an extraordinarily high rate, estimated at roughly 100 times faster than a typical stellar wind. And that gas is moving outward at speeds near 164 kilometers per second. When gas expands rapidly into a lower pressure environment, it cools. In the Boomerang Nebula, the outflow is so fast and so sustained that the gas cools faster than the surrounding radiation can warm it back up. The expansion rate outpaces the heating rate from the cosmic microwave background, driving the temperature below 2.7 Kelvin. The nebula is not simply cold. It is actively racing ahead of the universe's own thermal floor. The observational evidence for this comes from multiple instruments and methods. Early radio observations using the Swedish-ESO submillimeter telescope in the 1990s detected the nebula's unusual absorption signature against the cosmic microwave background. The cloud was absorbing CMB radiation rather than emitting it, which is only possible if the gas is colder than the background itself. That single observational fact is what placed the Boomerang Nebula in a category of its own. Later, the Hubble Space Telescope provided high-resolution optical imaging, revealing the asymmetric, boomerang-shaped lobes that give the nebula its name. More recently, observations from the Atacama Large Millimeter Array, ALMA, offered a more detailed picture of the nebula's structure, suggesting the outflow geometry is more complex than early images implied, with a round inner shell embedded within the asymmetric outer lobes. But observational limits matter here. The 1 Kelvin temperature estimate comes from modeling the radio absorption data, not from a direct thermometer. The measurement depends on assumptions about the gas density, composition, and the uniformity of the outflow. ALMA's higher resolution data complicated the picture somewhat. indicating that the coldest gas may be concentrated in specific regions rather than distributed uniformly across the nebula. The precise temperature structure is still being refined. What the evidence firmly supports is that some portion of this nebula is colder than the cosmic microwave background. The exact spatial distribution and minimum temperature carry meaningful uncertainty. There is also the question of the nebula's future. Protoplanetary nebulae are transitional objects. The central star is still losing mass, still driving the outflow. But that process will not continue indefinitely. As the star exhausts its outer envelope and the mass loss rate drops, the expansion will slow, the cooling mechanism will weaken, and the surrounding CMB radiation will gradually warm the gas back toward 2.7 Kelvin. The Boomerang Nebula's extreme cold is not a permanent feature of the universe. It is a brief thermodynamic accident, a window in time when the rate of expansion happens to exceed the rate of radiative heating. On cosmic timescales, this window is narrow. We are observing it at precisely the right moment. The leading explanation, supported by the radio absorption data and consistent with the ALMA observations, is that sustained high-velocity mass loss from the central star is the primary driver of the sub-CMB temperatures. No competing hypothesis currently fits the observational data as well. Alternative explanations involving unusual gas chemistry or external cooling mechanisms have not found support in the evidence. The adiabatic expansion model is not merely the best available explanation. It is the only one that accounts for both the absorption signature and the observed outflow velocities. What would strengthen or falsify this picture? More precise ALMA mapping of the temperature distribution across the nebula would help confirm whether the coldest regions correspond to the highest velocity outflow zones, as the adiabatic model predicts. Detailed spectroscopic measurements of the gas velocity field would allow tighter constraints on the mass loss rate and expansion history. If the coldest gas turns out to be spatially offset from the fastest outflow, that would challenge the current model and demand a revised explanation. Monitoring the nebula over time could also reveal whether the temperature is already beginning to rise as the mass loss rate evolves. There is something worth sitting with here. The coldest known place in the observable universe is not a product of cosmic isolation or ancient stillness. It is the result of violence, a star tearing itself apart, flinging its outer layers into space faster than the universe's own background radiation can respond. The cosmic microwave background is often described as a kind of universal constant, the thermal floor below which nothing natural should fall. The Boomerang Nebula is a reminder that local processes, operating on stellar timescales, can temporarily undercut even that baseline. The universe sets a floor, and then a dying star, in its final act of dispersal, briefly breaks through it. It also raises a question that the current data cannot yet answer. Are there other objects in the universe doing the same thing? In galaxies too distant for our instruments to resolve? The Boomerang Nebula was found because it is close enough to study in detail. The physics that produces its extreme cold is not exotic. It requires only a fast enough outflow and a high enough mass loss rate. Those conditions are not unique to this one nebula. Whether the universe contains colder places we simply haven't found yet is an open question, and one that future millimeter wavelength surveys may be positioned to address. The record may not be permanent. It may simply be the limit of what we can currently see. For now, the Boomerang Nebula holds the record. 1 Kelvin, colder than the void. A dying star, briefly, improbably, winning a thermodynamic race against the residual heat of the Big Bang itself.